Yeah.
And we want to do that because we want to predict epsilon.
Let's talk about how you talk to your customers. Whether you're notifying them when orders ship, providing support over the phone.
PDNN. I don't know whose fault that is, but it's just a thing that's happening right now. I have to do this. Probably most people. Maybe you don't even have to do that at all. I don't really know.
This is OutSystems, the most complete full-stack application development platform for professional developers.
So, let's see. So the other things, we can say min reward. Cool. The next thing we're going to do is self.tensorboard, and that's going to be a modified tensor board. I believe. Oh, I closed it. I believe that I'll put this in the code as well. Logdir equals. I think I use this as well in the Q learning stuff. So if you've done that series, you should have this code somewhere. But I'll put it in the text-based version too for this modified tensor board function. At some point, I'll show where to get it, and until I have it pasted somewhere reasonable, I'm not going to show it. So right now, I'm not going to add this code. But anyway, it just modifies TensorBoard to be a little more reasonable for the task of. I'm confident it's for Q learning, because the problem is we don't need as many updates to TensorBoard as TensorBoard wants to do. So yeah, because it's going to basically want to create a custom file per train session or train loop, I want to say, or something, or is it? It might be a per.fit, I think is the problem. I can't even remember. It's been too long. But anyway, regardless, we want to modify it so it stops doing that nonsense, and both for speed purposes and storage purposes. Anyway, we're going to at least specify the logdir, and it'll be model. It's an F string in case you didn't see that I threw that F there. Model name and then dash, and then the int value of time. Did we import time? We did. Great. Okay, so that specifies our TensorBoard. Then we're going to say self.target_update_count. Earnestly. False input. So anytime you take one of these models, like these pre-built models from TensorFlow, what we need to do is usually change the input layer as well as change the output layer. So the way that we're going to do that is we want to specify what do we want to use as input, what do we want to use as output, basically. So pretty much this is input, and then what we want to we could do a bunch of things, right? You could begin by saying model equals, and do the sequential model stuff, and then model.add, and then you start adding convolutional layers or dense layers or recurrent layers or whatever the heck you want to do. But what I'd like to do is straight use exception. So I'm going to say base model equals exception. We need to import exception, but for now I'm going to say weights is none. We don't want to start with any of their weights. We're going to say include top, false input shape. So top is that first layer. Since we're going to be using a different layer, we don't want to include that top layer. The input shape will be our height by width. So input shape will be image height, image width, and then it's by 3. And then before I forget, let me go to the top, and we want to actually import exceptions. So let's just do that. I don't really know if I want this at the end of all my imports or to separate Carla from Keros. I think I'll do it at the end, to be honest. From keros.applications.exception, we want to import exception. Done. Easy. So, okay. So anytime you take one of these models, like these pre-built models from TensorFlow, what we need to do is usually change the input layer as well as change the output layer. So the way that we're going to do that is we want to specify what do we want to use as input, what do we want to use as output, basically. So pretty much this is input. And then what we want to change is we're going to say x equals base model, and we're going to say dot output. Then we're going to say x equals global average pooling 2D times x. We want to import global average pooling. We'll do that in a moment. And then what we're going to say is predictions equals, and it's a dense layer. Again, we'll need to import that as well. It's 3 neurons. Activation will be linear, and that's multiplied by x. This is 3 because we have 3 options, right? We can go left, straight. Basically, we can turn left, don't turn at all, so go straight. Turn right. Or actually, it's not don't turn at all. And that, import that. We need to import. So input will be our height by width shapes exception, but for now I'm going to say weights is none. We don't want to start with any of their weights. We're going to say include weights is none. Because we will separate 3. Then we're going to say self.target underscore. update underscore counter. We're going to say that's equal to 0 for now. And then that basically gets updated every end of episode. Then we're going to say self.graph equals tf.get default graph. And we're going to do this in a separate thread. Again, we don't have to use threading, but we want to use threading, and we need to specify this because we want to use this in a separate thread. And we want to do that because we want to predict and we want to train in different threads. Okay, so now what we want to do is self.terminate equals false. This is one of the flags that we're going to use for our threads. And then we're going to say self.last log episode equals 0. This is just to help us keep track of TensorBoard as we're doing things relatively asynchronously. And then self.training underscore initialize.
Chị lo. Hả? Ora. 좋아.
Equals of TensorBoard as we're doing things relatively asynchronously. And then self.train and then dash and then the int now. And then that basically gets updated every end of episode. Then we're going to say self.graph equals tf.get default graph. And we're going to do this in a separate thread. Again, we don't have to use threading, but we want to use threading, and we need to specify this because we want to use this in a separate thread. And we want to do that because we want to predict and we want to train in different threads. Self.graph. Okay, so now what we want to do is self.terminate equals false. This is one of the flags that we're going to use for our threads. And then we're going to say self.last logged episode equals 0. This is just to help us keep track of TensorBoard as we're doing things relatively asynchronously. And then self.training underscore initialized equals false. Again, this will be another flag. Because we're going to be doing stuff in separate threads, we want to have these flags to sort of keep track of what we're doing. So this will be when we start running simulations. So now what I want to do is create our actual model. So define create model self, and in this case we could do a bunch of things, right? You could begin by saying model equals, and do the sequential model stuff, and then model.add, and then you start adding convolutional layers or dense layers or recurrent layers or whatever the heck you want to do. But what I'd like to do is straight use exception. So I'm going to say base model equals exception. We need to import exception, but for now I'm going to say weights is none. We don't want to start with any of their weights. We're going to say include top false input shape. So top is that first layer. Since we're going to be using a different layer, we don't include that top layer. The input shape will be our height. We need to import. What I like to do the sequence create model self, and in this case we could do bunch of things, right? You could begin by saying model equals, and do the sequential model stuff, and then model.add, and then you start adding convolutional layers or dense layers or recurrent layers. Whatever the heck you want to do. But what I'd like to do is straight use exception. So I'm going to say base model equals exception. We need to import exception, but for now I'm going to say weights is none. We don't want to start with any of their weights. We're going to say include top false input shape. So top is that first layer. Since we're going to be using a different layer, we don't want to include that top layer. The input shape will be our height by width. So input shape will be image height, image width, and then it's by 3. And then before I forget, let me go to the top, and we want to actually import exceptions. So let's just do that. I don't really know if I want this at the end of all my imports or to separate Carla from Keros. I think I'll do it at the end, to be honest. From keros.applications.x. Exception, we want to import exception. Done. Easy. So, okay. So anytime you take one of these models, like these pre-built models from TensorFlow, what we need to do is usually change the input layer as well as change the output layer. So we're going to do that is we want to specify what do we want to use as input, what do we want to use as output, basically. So pretty much this is input, and then what we want to change is we're going to say x equals base model, and we're going to say dot output. Then we're going to say x equals global average pooling 2D times x. We need to import global average pooling. We'll do that in a moment. And then what we're going to say is predictions equals, and it's a dense layer. Again, we'll need to import. Well, it's 3 neurons. Activation will be linear. And that's multiplied by x. This is 3 because we have 3 options, right? We can go left, straight. Basically, we can turn left, don't turn at all, so go straight. Turn right. Or actually, it's not don't turn at all, it's straight, go straight. So, okay, so those are our possible predictions. Then what we're going to say is the actual model that we want to use is model, which again, we'll also have to import. We're going to say inputs is equal to base model.input, and the outputs will be equal to predictions. So basically, it could have been base model.output, but we want to change a few things. We want to make it a dense layer. We could have made it pretty much just a dense layer, but we wanted to add the global average pooling here. Okay, predictions, done. Model.compile, and whoops, model.compile. Loss is going to be MSE for mean squared error. The optimizer we're going to use is going to be the atom optimizer. Again, we'll have to import that. Learning rate 0.001. And the metrics we wish to track. Accuracy. Okay. Return model. And we're good. So we need to make all these imports. So we'll go up to the top. We'll say from keros dot layers, we're going to import dense. global average pooling. And then from keras.optimizers, I think. Import atom. Let me check on my notes. Make sure that's correct. Optimizers, yes. And then the other thing we want to grab is from keras.models. We want to import model. And I think that's everything. Again, we're going to find out if we're missing imports and stuff. That's not the most important or most challenging thing to figure out. But I think that's good. Let me just look real quick here. Let me fix this. This should also alert me if I'm missing anything. Looks like we're good. So, okay, that's done. Now we're going to do define. We're going to update replay memory self, and then with any transition, and I'll explain that in a moment. So a transition is going to basically contain all of the information that we need to train the model, basically. So, or specifically a deep Q learning model. So that is going to be the current. Let me just say this. Let me just throw in transition equals, and it's going to be. It's like a list, right? Well, it's actually, we'll call it a tuple because it's not going to change. You're going to have current underscore state, the reward. Nope. So I have notes. Action, reward, new state, and then whether or not we're done. So this has all the information that we need when we're going to actually like train models and stuff like that, and update the Q value, so to speak. So so that's what the transition is, and we'll need to know that even more so in a moment. But for now, all we're going to say is self.replay for memory dot append transition. So we don't really need to know what a transition is here, but very soon we will, because define train self, and this is where basically the magic happens. So the first thing we need to do is make sure we have enough replay memory to actually train. If we don't have enough replay memory, one, epsilon is likely very high. We're just doing random things anyways. It's not essential that we train on this. But we want to have enough replay memory, again, so we have enough information for this model to actually start learning anything useful at all. So the first thing we're going to ask is if the len of self.replay memory is less than the minimum replay memory size, then we're just going to return. We don't really want to do anything. Otherwise, we want to train, and the first thing we want to do is grab our mini batch to train on. So we're going to say ram.sample of self dot replay memory, and the sample size that we want is mini batch size. So that gets us our random mini batch. Now all we need to do is calculate our current states and then the future states so that we can actually do the training operation. So current, not caps, current states equals a numpy array of, and we're going to say transition 0th. Again, that's our current state, right? The 0th element. And when we get our future, it'll be 0, 1, 2, 3. So transition 3. When we try to get our future states. So transition 0 for transition in whatever that mini batch was. Now, that state, that's your observation. What's our observation? It's an image. What do we want to do every time we use images with neural networks? We want to divide by 255. So again, this is just our way of scaling the information. Before we were doing the scale operation in process image, but now we're going to add it here. So current states, cool. So then what we're going to say is with self.graph as default, we are going to specify our current cues list is self.model. Pay attention to model versus target model. Self.model dot predict, and then we want to predict based on the current states and the batch size that we want to use is whatever our prediction batch size that we set. We actually have that set to 1 right now. Yeah. But later we could try something bigger. At least for me personally, this is a super heavy GPU, CPU, and RAM task. It is all of the things, so it's very challenging to run. So anyway, current queues list, let's go ahead and spell that correctly while we're at it. Okay, so now that we've done that, we want to do this future queues. So future queues is going to be very similar to this. So in fact, I'm going to copy, paste. This could bite me in the butt. So I guess new current states. That will be transition 3 for transition in mini batch. With self.graph as default, that's fine. Change this to be future queues list, not self.model, it's self.target underscore model, and it's not current states, it's new current states. I think that's good. Let me know if you spot an issue. Capital X equals empty list. Lowercase y equals also empty list. Now what we want to do is we're going to enumerate over all of our batches and do our training. And basically we want to make sure we only do our training when basically, well, we need to create the Q values, and we only want to do that if we didn't, because there can be no future, so we only want
起龙，妈的！你妈知道了，我打死你！哟。小龙，过来。哎，这小锅给你挪过来，给我学习。过来。啊！
update the queues when we have a future state. So if it's a terminal state, so i.e. we crashed, then we actually set the queue to be whatever our reward was just now. But if we didn't crash, we actually want to set the queue based on that queue formula. So what we're going to say here is for index, comma, and then again, this will be that entire tuple, this right here, the entire transition. So for index, all this stuff, in enumerate whatever mini batch is. Oh, don't forget our colon here. Okay, for that, then what we want to say, we want to make sure we're not actually done. So if not done, max underscore future queue equals np.max future queues list for the specific index, new queue equals reward plus discount times max future queue. If we are done though, the new queue is simply equal to that of reward. Again, this concept has been explained already in the reinforcement learning series, but we all, including myself, sometimes need refreshers. So, next. Is current queues equals current queues list for this index, and then we're going to current queues for that action that we took, new queue. So this is how we're going to update that actual queue value. And then, once we've done that, x.append current state, y.append current queues. Okay, so for okay, this needs to be tabbed over. So that was almost. A me in tears moment in the future. What's going wrong? Okay, so, all right. Now that we've done that, we're going to throw in just some code for the tensor board. So log this step equals false. We want to make sure we're logging only per episode if self tensor board dot step is greater than self dot last logged episode. Log this step. We'll set that to equal to true. Self dot last log episode equals self dot tensorboard dot step. Okay, so now that we've updated these values and we've made like x and y and all that stuff, what we need to do is actually fit the x and y. Current state is 255. So when we go and do that, so let me pull down to here. Current state, I just have to check. Okay, so current state. Sorry, I just want to make 100%. So current state is always going to be here. So it has not been divided by 255. Yeah, had to make sure. So what we want to do now is we're going to say with self.graph.as default. We are going to say self.model.fit the NumPy array of x div 255 np array of y. The batch size will the training batch size. We're going to set verbose to 0, shuffle to false would be unnecessary. Callbacks we're going to set to be self.tensorBoard if log this, if log this step, else none. So callbacks will be self.tensorBoard if we're trying to log that step. Otherwise, no callback.
Let's talk about how you talk to your customers. Whether you're notifying them when orders ship, providing support.
Okay, so now what we want to do is update that log this step stuff. So if log this step self.target update plus equals 1, then if self.target update counter is greater than update target ever, what we want to say is self.target underscore model dot set weights equals, dot set weights to self.model dot get weights. So again, it just becomes a copy of that initial model, or the actual model. Then self.target update counter equals 0. Cool. Okay, so that's our train method. Hopefully that's good. I suspect we're going to have a lot of issues, but that's okay. Let me decide. I think we can finish the agent code here. We don't have that much more to do. So first of all, define get queues. Keys for self and state, so we want to pass a state, get 2 values, so that's just going to be returned self.model.predict num. Array of whatever state happens to be passed, and then we're going to do a reshape -1 and then state.shape div 255 and we are expecting that to be a single thing. So again, as always, prediction predicts, you pass a list, you get a list back. In this case, when we get queues, we're just getting one at a time. So we're going to grab the 0th element. State.shape, this will just be our image shape. This has a little bit of Daniel sprinkled into it, and I guess he likes making ugly code. Hope you're watching. So now, what we're going to do is define train in blue. Thanks, Daniel. You're doing great. So in case you don't know what this means up here, this is just unpacking the shape of state, which is our observation, which is height, width, 3. So 486, 64. This tutorial is going on too long. Anyway, it's the height width times 3, or by 3. So anyway, it's just unpacking. It's a nice succinct way to code it in there, but at a quick glance, it doesn't. Yeah. Anyway, continuing on. Train in loop. Basically, so far we actually haven't seen this threading that I was referring to that we're going to wind up needing to do, but this will be the first time we really see what truly is going on here. But recall, we want to train and predict in different threads because we don't want training to slow down predictions. We want to be able to make predictions as quickly as possible, and we want to train also as quickly as possible. So the way that we're going to do that is a couple of ways. First of all, initially, for whatever reason, TensorFlow, again, I don't know if it's TensorFlow's fault, is it NVIDIA's fault, is it CUDA's fault, I don't know. But the very first time you actually start training, or the first time you try to do a prediction, it's really slow compared to subsequent predictions. That's why if you want to put something in the cloud, for example, that actually is like some sort of API that does predictions, you want to make sure you're predicting in some sort of infinite loop. You would never want to like reinitialize everything all over again, because you're not just initializing and you're not just like loading in the weights. For some reason, you're also doing some other thing that I don't know what it is, but that first prediction is slow. So what we're going to say is we're just going to randomly do a fitment, and then what we're going to do from there is do, sorry, I said prediction, but I meant it as well. It's prediction or train. It's just that first thing takes forever. Anyway, the first thing we're going to do is we're just going to do a quick fitment on nothing, and then we're going to fit from there. So we're going to say x equals np.random.uniform, and we're going to size equals 1, and then we're going to do, what is it, m height, m width, and then 3. How come you didn't unpack there, Daniel? as type np float 32. Then what we're going to say is y equals np.random.uniform. There we go. Size equals 3, and then dot as type. np.float 32. So again, we're just gonna make it up. We just want to do a quick fitment on something. So with self.graph.as defaults self. Fit x, y, verbose, false, batch size, 1. So once we've done that, we will say self.training initialized is equal to true. And then we're going to just initiate this while true loop that goes on and on and on. So while true, if self.terminate, then we will return and we're done. Otherwise, we're going to self.train, and then we're going to throw in a quick sleep 0.01. And we're done. So later, we'll get into training and loop and how all that's going to work. I think I'll save that for the next tutorial. This tutorial is quite long. I think I might have reached 40 minutes on that one, so we're done. Okay, so if you have questions, comments, concerns on the code up to this point, feel free to leave them below. You can also come chat with us, hang out in the Discord. That's discord.gg/syntax. Also, shout out to recent channel members who are not recent, who have been with us for many months. 8 months, Gene Git, Michael Severson, and Ravi Krishna. 9 months, Uday Manshanda, Bingley, Metanoia, Reginald Roberts, Bill Fallensby, Erica Bow, Tibiru Gochu, Mikesi Weki. If I've mispronounced your name, feel free to let me know in the comment section, and I'll try to get it right next time. Anyways, in the next video, what we're going to do is, I haven't fully decided. We should be able to finish all of the code, and then maybe what I'll do is I'll show you at least where I'm at now with this code, and then maybe I'll continue tweaking things or working on things and kind of share updates as we go, because I hate to be the bearer of bad news, but this is probably not good enough. For example, our reward function is probably no good. We're going to need something a little more complicated than what we've got. We've got a lot of variables going on here. There's also highly likely to be some sort of bug in the code, or some sort of assumption that I've made that is incorrect. There's just so much going on here that it's highly likely this does not work out of the gate, and instead it's going to take a lot of tweaking and coming back to it to really figure out what's best. But you can feel free to play with everything. Maybe you can come up with something better than even I can or me and Daniel can. So anyways, that's it for now. Next tutorial, we'll wrap all this up and at least show it hopefully starting to run and hopefully train to some degree, and at least make sure that everything is working, like epsilon decay, and hopefully loss is doing a thing. We're not getting like perfect accuracy or any of the other red flags, and we should hopefully see that after training for a few hours, average reward is going up, that sort of thing. We want to know that something is happening. Okay, so
Invest in your future with Simply-Learn's postgraduate program in DevOps in partnership with Caltech's CTME.
Hey, how's it going, everyone, and welcome back to another video. We've got a fun one in store today. We're going to go through
Invest in your future with Simply-Learn's postgraduate program in DevOps in partnership with Caltech's CTME. Learn in-demand DevOps tools including Docker, Kubernetes.
What's going on, everybody, and welcome to part 5 of the self-driving cars with Carla, TensorFlow, Keras, and other things. Basically, we're trying to do reinforcement learning here. Okay, that's the tutorial series. Where we left off, we created the car-env, and we created the agent, and now we're just going to tie everything together and actually hopefully start the training process. So with that, we're going to make a couple of imports here real quick. Import TensorFlow as TF, import keras.backend.tensorflow_backend as, backend, and then to Keras, we're just going to tie everything together and actually hopefully start the training process. So with that, we're going to make a couple of imports here real quick. Import TensorFlow as TF. Import keras.backend.tensorflow. Underscore backend as backend, and then from threading, we'll import capital T threading. Those imports, we're going to go to the very bottom, and we're going to start our main, dare I call it a loop, but really if statement. If name equals done. So if this is the script that's running, we're going to just set, we'll say FPS is 60. You'll see why in a moment. We'll wind up probably, this will have to be tweaked. This is a we wish kind of number. We're not going to get 60, but anyway. And then ep rewards, we'll just prime that with -200 to begin. Random. Dot seed 1, we're going to just set some random seeds. Basically, this is just for repeatability. mp.random dots seed 1, and then the TensorFlow dot set underscore random underscore seed. Set that to 1. This is so we get as repeatable as possible things, so we can kind of compare and debug. So now what we want to do is, most people probably don't have to do this, but you're running multiple things on your GPU, or you're like me and for some reason your GPU really wants to allocate more memory than it possibly has. We're going to do GPU underscore options. Also, if you want to run like multiple agents, you have to do this. We're going to say tf.gpu options, and then we're going to say per underscore process underscore GPU underscore memory up. Underscore fraction, and then we're going to set it to whatever memory fraction is. So it's up to the bottom or the top here. Mine is set to 8. I'm actually going to downgrade that to 6 even. For you, you can probably say 1.0 or 0.9 or whatever. Especially if you want to continue using your computer while an agent trains, you can set it even lower than that, and then you might not even notice that you've got training going on in the background unless you try to play some video game or something. So anyway, that's how you can tell basically TensorFlow. It's pretty obvious, but this is per process. So basically per model, each model will, in my case, use 60%. So if you wanted to have like 5 models, each model would have to use less than 0.2, right, for your memory fraction. So, okay, cool. Coming down here, that's the GPU options. Now we need to set that. So we're going to say backend.set underscore session, tf.S session. Big equals tf dot config proto, that's title cased, and then we're just going to say GPU options equals GPU options. Cool. So TensorFlow now will hopefully listen to me. Okay, now that we've done that, we're almost ready to start training, but we need somewhere for our models to go. So we're going to say if not os.path.is dir. Come on, oh dear, models. So if that path does. Exist os.makeDirs models. Done. Then we're going to define our agent equals eqn agent, and then we need env. That's going to be car env. Cool. So once we have that, we're ready to initialize the trainer. So we're going to say trainer underscore thread equals T thread target will be equal to agent.train in name equals true. And then trainer thread dot start, and then while not agent dot training initial. So until that flag is true, we're just going to time.sleep for a minimal amount of time, basically just wait here until we're ready to go. And then just like if you recall training loop here, we do a model.fit to kind of prime the fitment, so because the first one's going to take so long and then we engage in our infinite loop. We kind of want to do the same thing with the predictions. So because your first prediction will also take an exceptionally long amount of time, so we're just going to say agent.get underscore queues np.ones, and we're going to say env.im actually, now, hold on, this might be different in my notes. Let me go to tippity top here. No, we definitely have, well, we've got car env, so env dot, im height, and then comma, env dot im width. I still see this im versus image. That has me a little cautious at the moment. I think we've got an error there. Image height. So we got a couple of those image height, and I don't. Yeah, and we don't have any definition for those. So that would have been a problem. So what we want to do is I'm going to do Control H. I'm going to search for image height, and I'm going to replace that with im height. image, Control H. I'm gonna search for image height, and I'm going to replace that with im height. Replace all, and then I'm going to do the same thing for width. So width. That needs to be image width, im width. Cool. So, that would have bitten me. Don't worry, we'll have other errors that I'll hit. I'm positive. So, in height, in width, and then 3. So again, it's just going to get some key values for something that is totally irrelevant and not important in any way. Totally just dribbled. You saw nothing. Okay. Now what we want to do is basically start iterating over however many episodes we have. So we're going to say for episode in TQDM. Do that import TQDM? No. From TQDM, we're going to import TQDM. Back to the bottom. DM, we're going to import TQDM. Back to the bottom. Okay, for episode in TQDM, range 1 to episodes plus 1. And then we're going to say ASCII equals true. This is for our Windows brothers, so it looks pretty still. And then, so if you're on Linux or something, you don't have to say ASCII equals true. And then we're going to say unit is episodes. I forget what the default unit is, but at least it'll make sense. Episodes. Okay. Then, what we want to do is, let's say n dot collision underscore hist is going to be an empty list, and trying to decide if I want to put this. No. So this is where our collision sensor is going to start slapping in information. The next thing we're going to say is agent.tensorboard.step is equal to episode. So you've got steps, and normally what would happen is every frame would in theory be a step to TensorFlow, because every frame it would even be, well, if the batch size, anyway, it would at least every frame be a step. Let me put it that way. And we don't want that. That's way too absurd. So instead, we're actually saying, okay, every episode is a step. So now TensorBoard will show us basically a plot per episode instead of intra-episode. Anyway, continuing on. We're going to say episode underscore reward is equal to 0. And then step equals 1. And then we're going to say current underscore state equals m dot reset. So that gives us our first observation ever. Done will be false to start. And then episode start equals time.time. I'm getting over a cold, and the brain is still a bit foggy. Okay. So for every single episode, we at least set these values, we do an env reset, and now we start the actual while true, which basically is while not done, pretty much. But just because the done flag gets triggered, we want to do a couple of things and then exit immediately. So we're actually just going to, we want to dictate exactly where we exit. So anyway, we're just going to use a while true, and then if done at a specific point, we click. So, while true, if np.random.random is greater than whatever the epsilon value currently is, we're going to say action equals np.argmax agent.get_queues for the current state. But if that's not the case, we're going to say action equals np.random.randint between 0 up to 3. And then we're going to say time.sleep1 divided by FPS. So what's the deal there? So again, we're not going to actually get 60 frames per second. We're probably going to get I don't know, 20 to 30 on a really nice GPU and then 4 on a bad GPU. Or really probably none. You can't run Carla on a bad GPU, unfortunately. So when epsilon is really high, you're going to take a lot of random actions. Well, taking a random action, we get to avoid the agent.getQueues. So we get to avoid doing a .predict. So we get to avoid using the neural network at all, which is what's going to take time. Whereas a random.randint, this is like a nearly instant operation. It's going to happen really quick. So this is problematic because we actually want the agent to, whether it takes a random action or takes a model action, we want that time that it takes to be about the same, right? Because otherwise, because frames per second really helps the model. So the higher the frames per second, the better the model's probably going to behave. And if you take a random action, but like a split second later that is way quicker than normal, you take a model action, it's just not good. We definitely want the frames per second of either one of these to be as close as possible. So the way that you can eventually figure out what frames per second you're getting is at least wait until your memory replay is filled up and you're actually making predictions, and then set your epsilon to 0, and then read your frames per second. That's how many frames per second you'll get for if you predicted all the time, and then you can set this value. You can also guess. I mean, it's probably unfair of me to say 60 at all to even start with. No one's going to get 60. I don't think I would get 60. So maybe put 20 or something like that. I'm going to put 60. Well, I'll just stick with 20. That's fine. We're not going to get. I actually might get 20 on this machine, but it's unlikely. But anyway, I'll go with that. That's fine. So all right. Once we've done that, so while true, we take our action. The next thing we want to do is actually do new state, comma, reward done underscore, because we don't have a value for that. We're going to say env.step based on whatever action we decided to take. And then we would come back here, true, and then for actor in n.actor_list left. list actor dot d okay, so let me break this apart. So this is what we'll do during the episode. So we're just updating replay memory, and then also take note. So here we're making our actual predictions, and then we're updating the replay memory for like the target model and all that. And then you might be wondering, well, what's going on in the target model? Well, don't forget, we are training in loop here for that actual target model. So that's off doing its own thing. It's taking in information from where? Well, from our games where we were actually updating the replay memory. So, so basically, this is doing everything at this point that we need to.
睡着了，高兴。4.5附近多。
We both to play and train, so predict and train at the same time. Okay, now we want to track some stats, but I think I'm gonna not type that out because one, I think we've typed it out before, and two, it will waste time. So we do have some stats that we want to collect, and I'm trying to decide if there's anything else here in the text. So let me pull up our text-based version.
Deep learning and machine learning both off.
Did I not post? I must not have posted the. Oh no, I know what that is. So here, I am. I suppose we could take, because we need to take this, and we also need to take our tensor board script. So I'm going to grab both of those things. So I'll put a link in the description for both of those things. And then basically when you get there to part 5, so just in the description there will be a link that says like text-based version. There'll be sample code and text-based tutorial or something along those lines. The first little block is the code that we started with, but if you continue scrolling down, usually it's at the very bottom, but actually at the very bottom I've got a play script for us. So go to the very bottom, skip that first script, boom, there's your second script. And to be honest with you, I'm just gonna, first we'll copy this bit. So the actor destroy we've already done. I'm gonna come over here, pasta, I'm gonna tab this over. I'm a little cautious as to why that was where it was. That's probably why we're not actually accepting anything at the moment, so that's why that was tabbed over. So anyway, yeah, let's talk about this right before I just copy and paste and do nothing. But this is all code that you've definitely seen before. Same thing here, because everyone watching has done the reinforcement learning series. But basically, we're just collecting information like what was the lowest reward, what was the highest reward, and what's the average reward. So we're kind of hoping average reward ticks up over time. In this case, max reward should also tick up over time. We got a long way to go before our maximum reward will ever max out. And then min reward, this should also hopefully go up over time. So even our worst episode improves, right? But something tells me probably min reward also, if never, min reward is going to be really challenging because sometimes it's just going to have a bad spawn and crash immediately. So I don't know. Also. cars I've seen it happen where we'll spawn and then like an NPC, if we use NPCs, drops right on top of it. There's nothing you could have done, so you'll still have to deal with that. And here, again, based on any metric you want. So in this case, this is just as long as the minimum reward is greater than some value. I actually. I would go with average reward now, but anyway, you can set this to be whatever you want. So you can say if average reward is such and such and min reward is greater than some other value, whatever, feel free to set that however you want. It'll save the model. And then before we exit, the other thing we definitely want to do, basically we need to do these last 3 lines. So so this is going to run, right, for every episode that we have. And then when we are completely done, we want to clean up to some degree. So I'm going to copy and paste in these 3 lines. And what's happening here? So here, have, this will terminate our agent. This completes basically the threading, and then finally here we save the model regardless of whether or not we hit this. So the first time I actually ran this script, it actually looked pretty good, and I didn't save it because this thing wasn't met. Well, we're only going to run 100 episodes. Yeah, just for testing purposes, I'm going to make sure the script actually runs. And anyway, when I ran it the first time, I didn't save the model, and I was like, dang, that was actually a pretty decent looking model. So, and actually, I think I saved, yeah, I put both. So I'll show the tensor boards in here, and we'll talk about that in a second. But the first thing I want to do is actually make sure this script can run at all. So one, make sure you've got Carla up and running, because if you don't have that, it's not going to work very well. And then two, we need to run the script that we're actually working on. So API examples and Tutorial 5.pi is what we're doing. Pi dash, don't forget 3.7, tutorial, whoops, 5.pi. Okay, let's run that. Of course. Oh, right. Okay. We actually, a positional argument is, and let's try again. Is it thread? Actually, that was not an expected error. Is it thread? It's probably thread. That makes a little more sense, but let me confirm that. Yeah, it's just thread. What a noob. Now I gotta fix threading. Let me find where I actually typed threading from. Oh, I imported thread. But then down here, oh, did I actually type thread correctly? Yes, I did. Okay, carrying on. Hey, we're getting some information here. It's kind of going off screen, my apologies. I'm sure we'll hit an error at some point, right? Surely we gotta hit an error. than just this. Find one. TensorBoard. I don't remember if we brought that in or not already. Kara, I don't see it. So whoops. Again, this is yet another thing that is coming.
TensorFlow has no attribute. GPU option. Whew. Toma. 吃去吧，去吧。Saving your environment using the condom. Activated. 你是不是又拉屎了？嗯？他妈的，还把屎拉到这儿！我操，服了！九，你们又拉屎了啊！